Hi everyone. So at this point you would have reviewed the PowerPoint slides, and based on what you learned from the slides and what you've seen when we looked at the emission spectra for different elements, you now know that electrons can be located both in the levels we learned about in grade 11, n equals 1, 2, 3, and in sublevels, S, P, D, and F. So we can describe where exactly electrons are located in greater detail by either using electron configurations or energy level diagrams, which is what we're going to discuss in this video. So in order to write an electron configuration for any given atom, we're going to use the Aufbau diagram, and this is the one that's listed here. And basically what you need to do in order to figure out where things are going to go in terms of electron placement, you will follow the tip of the arrow to the tail rule. Now we're remembering that the s orbitals can hold up to 2, p can hold up to 6, d can hold up to 10, and f can hold up to 14. Now there are a couple of tricks here, and I'll discuss that with you when I get back to class in terms of the filling order. It doesn't just go in a sequential, sensical order. So let's take a look at an example. We'll do nickel first. Nickel with 28 electrons. So we're going to start at 1s, and we're going to imagine, even if this was sort of a representation of the atom, that this would be where the nucleus is located, and then we're moving away from the nucleus. Okay, so we need to fill each of the orbitals first before we move on to the next one. Okay, so that's basically Hund's rule, filling the closest locations or sublevels first, and then moving away from the nucleus. So we're going to start with 1s2, follow our tip to tail rule, and we're going to get to 2s2. The numbers signify the number of electrons, okay? So we've got 4 of the 28 accounted for. Follow tip to tail again, and I won't keep writing this because it's getting a little messy. 2p, and p holds 6. Keep going, 3s2. Keep going, 3p6. Okay, and at this point now, we have got 10, 18. We need to keep going. So after 3p, we have 4s. Well, let me do that, so I'll do it down here, 4s2. So we've got 2, 4, 10, 16, 18. We still need 28. After 4s, we go to 3d, 10, because again, d holds 10. Okay, so let me just write that out a little bit neater. Okay, so the superscripts are the number of electrons, which for nickel need to add up to 28, and they do. Okay, so that's one way to depict, and obviously this is much greater detail than just drawing a Bohr diagram with dots. Now we can also draw an energy level diagram, and I'm going to suggest that when you do an energy level diagram, you always write out the electron configuration first. So for calcium, we're going to use the Aufbau diagram again. We're going to use Hund's rule, so we'll fill the orbits or the levels that are closest to the nucleus first, and then we're going to move out. So 1s2, 2s2, 2p6, so I've got 2, 4, 10 electrons accounted for, 3s2, 3p6, 4s2. And total, there's 20 electrons, so I've done this properly. Okay, so for the energy level diagram, what I want you to do is you're going to create an x and y axes, and we're going to imagine that this is the nucleus. Okay, and as we move away from the nucleus, the electrons need to possess greater energy to move away from that positive attraction as they are negatively charged. So what I want you to do is, and moving forward, you don't have to do this, but just so you have a visual, I like to see all of the orbital or the sublevels arranged one on top of each other. But as we move away using the Aufbau diagram, we're going to stagger the different levels. So each sublevel will be depicted by a line. So the 1s sublevel is going to be depicted by a line. So I have 1s2 here. I'm going to draw my 2 electrons. One electron is going to have an up direction, and the opposite is going to have a down direction. Okay, and this is following the Pauli exclusion principle that no two electrons can have the exact same location. So we'll talk a little bit more in class about why they exist together, but if you think about your Bohr-Rutherford diagram, we always had you drawing them in pairs. Electrons have a unique spin capability that allows them to exist in close proximity even though they have identical charges. Okay, so I've taken care of 1s2. I'm going to run out of room at this rate. Let's see. So 2s, there's the 2 electrons. Now I'm going to move over, but you'll see that I'm slightly staggering the lines for p higher. Each of these lines can hold up to 2 electrons. And because p holds 6, I'm going to fill in 6. I'd like you to singly fill like I just did, and I will explain that in a second as well, why I did that. So 2p2, 2p6 is done, 3s2, 3p6, single, 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 double, double, double. Sorry about the squishiness, and 4s. Okay, so if I hadn't have drawn all over everything, you can see that each level is a little bit higher. So this one goes up, this one goes up, this one goes up. So all my S's are in a line, my P's would be in a line. If I had D's, they would be started in this proximal space, but higher up, and F, etc. Now, why do we singly fill? If you find that you've got an example of an atom that has perhaps 3 electrons in a p orbital, it is much more stable to have a single electron in each of these areas than to have something that looks like this. Okay, and then nothing in that third location, quote unquote. Okay, so I'd like you to follow this single fill and then double up if you've got enough as we move forward. Okay, so I'm going to stop now, and when I return to class, we are going to go over some examples and just clarify any questions you might have. Feel free to watch the video more than once, or you can use your textbook. There's texts at the back of the room that are available that can also help clarify any concepts that you might have questions about.